I am Ayush Pandey and I'm one of the co-authors of the paper Refine and Align Confidence Calibration through Multi-Agent Interaction in VQA, which has been accepted at AAA conference in special track of AI alignment. In this video, I will going to explain this paper. Let me begin by briefly introducing the task. Visual question and answering is a multimodal problem where a model is given an image along with a natural language question and it is prompted to produce an answer. What makes VQA particularly challenging is that model must jointly combine visual perception, language understanding, and reasoning all within a single system. Because of this complexity, VQA has become a standard benchmark for evaluating visual language models and is increasingly used in real-world application. Let us look at a concrete example. Here, the model is given an image, this time a map with a highlighted region, along with a question which continent is highlighted. The model must interpret the image, understand the question, and select the correct answer from the available option. In this case, the model should answer North America, which is the correct answer. Now consider a different setting where VQA is used in high-stake domains such as medical imaging, where the confidence is just as important as correctness. In this example, the model is given a chest X-ray image and asked a yes/no question. The model predicts no with a confidence of 0.95, and this answer is incorrect. In a medical setting, a wrong prediction made with 95% confidence is far more dangerous than a wrong prediction made with low confidence. So the problem is not just whether the model is wrong, but whether it knows it might be wrong. This mismatch between confidence and correctness is what we refer to as miscalibration, on which we work. So far, we have discussed the standard VQA setup where a single model produces an answer. More recently, VQA models have moved towards agentic architectures where multiple interactive agents collaborate to solve complex visual reasoning tasks. The example on right illustrates a typical fixed role setup where different agents play contemporary roles such as gathering evidence, reasoning, and integrating information. These systems often achieve stronger reasoning than single VLMs, but these agentic systems also have some limitations. First, most existing VQA systems rely on static interaction protocols. The roles, the number of agents, and interaction patterns are fixed. This leads to limited adaptability. Easy and hard questions are treated similarly. More importantly, none of these methods optimize for calibration explicitly. They focus on improving accuracy but do not control how confident the model should be in its prediction. This becomes a serious issue when we look at real world applications, where VQA systems are increasingly used in high stake domains like medical imaging and autonomous driving. In such settings, accuracy alone is not sufficient. A system must know when it is likely to be correct and when it is uncertain. Overconfident but incorrect predictions can mislead clinicians, trigger unsafe decisions, and ultimately reduce trust. To understand the calibration problem, we use reliability diagram. A reliability diagram visualizes how well a model's predicted confidence aligns with its actual accuracy. The x-axis represents predicted confidence, while the y-axis shows the empirical accuracy observed for the predictions. The diagonal line corresponds to perfect calibration, where confidence exactly matches the accuracy. The blue bar indicates the observed accuracy in each bin, and the red shaded region highlights the gap between predicted confidence and actual accuracy, which represents miscalibration. When the bar is below this diagonal line, it shows overconfident as shown in this figure. And when the bar are above the diagonal line, it shows underconfident, which is shown here. So here we show state-of-the-art visual language model performance on science QA dataset. The reliability diagram shows miscalibration. The bars are significantly below this diagonal line, showing overconfident predictions. Whereas in this particular case, VQA radiology dataset, the bars are above this diagonal line, which shows underconfident predictions, and hence these are miscalibration. Now, let us briefly look at how calibration has been addressed in prior work. First is the selective answering. These methods do not improve calibration, they only avoid answering. Other are the train time calibration, which basically combines the focal loss to improve the calibration. Other is this Bayesian approaches, which basically uses variational fine-tuning to for model uncertainty via posterior weight distribution. However, these methods have limitation like they require fine-tuning and they are computationally expensive. Hence, while agentic systems have been explored for reasoning and calibration has been studied independently, multi-agent collaboration for post-hoc calibration in VQA remains largely unexplored. Our works therefore address this gap by introducing a multi-agent framework in two complementary ways. First, we introduced a multi-agent debate framework that performs post-hoc calibration. Specialized agents generate diverse answers, while generalist agents critique and refine answers, leading to more robust prediction. Second, we introduced AlignCal, a calibration-aware training loss that directly minimizes an upper bound on calibration while preserving accuracy. Together, calibrated agents and deliberation debate yield substantial improvements in EC and AC values across various dataset benchmarks. So now let me explain the proposed diagram. So it consists of two stages. In stage 1, we query specialized agents fine-tuned with our AlignCal laws, each with different prompting strategies such as chain of thought, search-based prompting strategies, self-ask, and knowledge-based prompting strategies. Each agent independently predicts an answer along with the confidence. In this example, three agents predicted cardinal fish with confidence 0.85, 0.70, and 0.95, giving an average confidence of 0.83. However, one agent predicted black hole with a confidence of 0.90. Now, if you use simple majority confidence, the system would incorrectly choose black hole because zero point 0.9 is higher than the average of 0.83. This is the classic calibration failure. A minority but overconfident agent overrides the collective evidence. Stage 2 is specifically designed to resolve such failures. Here we introduce a set of generalist agents that engage in the debate process. Each agent is initialized with a stance sample proportional to how many agents supported that answer in stage 1, so that the majority opinions are preserved but minority are still viewed. Each agent is shown a summary of arguments of for or against each candidate answer. For example, the agent predicted black hole is shown why other agents supported cardinal fish. Similarly, the agent supporting cardinal fish is shown why that particular agent supported black hole. After reviewing both supporting and opposing arguments, each agent produces a revised answer with a revised confidence score. Hence, after deliberation, we aggregate the refined output using majority voting over the agents. In this particular example, the system correctly converges to cardinal fish with a confidence of 0.91 that better reflects the true likelihood of correctness. Now we highlight the effect of AlignCal and debate strategy. This table basically illustrates how confidence estimates evolve as we go from raw VLM to AlignCal fine-tuning and finally to agentic debate. If we look at the base VLM call, the COT agent predicts black hole with almost 100% confidence, which is the classic case of overconfidence. At the same time, knowledge agent is only 0.53 confident, despite predicting the correct answer. Now, after AlignCal, confidence become more reasonable at individual agent level. Under confident agent increase their confidence. For instance, 0.53 goes up to 0.85, while overconfident predictions are softened, such this one goes to 0.90. AlignCal thus correct them at agent level, while this debate strategy then tries to refine the confidence globally through the debate process as we discussed in the previous slide. So here is just the summary of the stage-wise methodology that we have discussed in the previous slides. So now comes up the second contribution, AlignCal loss. So we introduce a AlignCal, a calibration-aware loss that directly targets misalignment between confidence and correctness. Here, Pmax is the model's top predicted confidence and Py is the probability assigned to the ground truth class. Now, if the model is correct, meaning Py is high, then the loss penalizes low confidence, encouraging the model to be more confident when it is right. So, AlignCal simultaneously penalizes overconfident incorrect predictions and underconfident correct ones. Most importantly, the loss is not a heuristic. It is derived as a smooth differentiable surrogate to upper bound calibration error, which is recently proposed in the literature. So basically, upper bound calibration error measures how misaligned confidence is correctness on a per example basis. This expression splits up into two cases, when the model is wrong and when it is correct. We can rewrite this more compactly as an expectation over a binary correctness variable t. Here t equal to 1 means that the prediction is correct and t equal to 0 means the prediction is incorrect. Now we can rewrite the UBC by conditioning on the input x, and we can apply the law of total expectation, which introduces QX, which represents the true probability that the model's prediction is correct. Now, if we knew QX, minimizing this expression would directly minimize calibration error. However, QX is unknown and non-differentiable, so we can't optimize UBC. Instead of QX, we substitute the model's own soft estimate of correctness, which is a probability assigned to the ground truth class Py. Hence, when we make this substitution, the resulting expression is exactly our AlignCal loss. Hence, in expectation, AlignCal is a tight differentiable surrogate to UBC. So this particular table summarizes calibration performance across VQA and ScienceQA. We can compare multiple calibration strategies such as post-hoc methods and train time methods using the standard metrics of expected calibration error, adaptive calibration error, maximum calibration error. Across both the dataset, our approach consistently achieves best or second best performance, shows the AlignVQA improves confidence reliability without sacrificing accuracy. These reliability diagrams provide a visual confirmation of the results. The base model shows strong miscalibration. Fine-tuning alone with focal loss improves calibration, while AlignCal substantially reduces this overconfidence. By aligning the confidence with correctness during training, the agentic debate further improves calibration, and combining both AlignCal and agentic debate yields a best reliable and well-calibrated confidence estimate. This slide highlights the individual and combined effect of our component. First, the agentic debate already improves calibration by reducing AC in AC. Secondly, AlignCal improves them at the training stage. Finally, combined strategy with the deliberated agents yield the strongest performances. Our ablation studies show that removing weaker agents actually improves calibration. In this case, when we remove the CO knowledge agent, the calibration improves. We have also studied the efficiency trade-offs. Increasing debate rounds degrades calibration, so we adopt a single round for both effectiveness and efficiency. While inference time is higher due to sequential execution, this is a practical limitation of our work and can be basically solved using parallel agent execution. To conclude, we introduce AlignVQA, a multi-agent debate framework designed specifically to improve confidence calibration in VQA. And the future work will focus on reducing inference overhead via selective agent activation and extending this to risk-aware high-stake applications. Thank you.